Okay, so you know that structure of the atom PDF you sent me. Wild stuff. We're going to try to break it all down and really trace, like, how scientists figured this whole thing out.
It's a journey, that's for sure. Imagine trying to understand something so small you can't even see it.
Right. So where do you even begin? The PDF starts with, like, what makes different elements unique and if atoms are really indivisible. Were they just, like, totally guessing back then?
Not entirely. Even before we had powerful microscopes and stuff, scientists were picking up on clues about charged particles just from everyday things. Think about, like, static electricity, that shock you get from a doorknob.
Or when your hair gets all staticky after you brush it. It's like suddenly the brush and your hair are magnetized or something, but instead of metal, it's, well, each other.
Exactly. Those everyday things, they were hinting at a whole hidden world inside atoms. That brush was actually moving tiny particles called electrons from your hair, and that's what caused that static charge.
So, like, from static cling, scientists started figuring out the atom. Seriously.
It's kind of cool, right? It shows how much we can learn just from paying attention to the world around us. Now, this whole idea of charged particles, it led to a really big moment. I'm talking about the discovery of the electron by J.J. Thomson.
And the PDF mentions something about canal rays being how they found protons. Honestly, that part kind of went over my head. What are canal rays?
Good question. Canal rays were important because they showed there was this positively charged particle. Basically, Thomson saw that they were deflected in the opposite way to electrons, meaning they had to have a positive charge. It was a huge clue.
So if electrons were negative, there had to be something positive to balance them out, right? Hence the proton.
Exactly. But here's the wild part. Protons, they're about 2,000 times heavier than electrons. Imagine a bowling ball next to a speck of dust.
2,000 times. So electrons are like whizzing around this massive proton. Why don't they just fly off?
That's what scientists were wondering. And that question, it gets right to the heart of how atoms are structured. But before we get ahead of ourselves, we need to talk about the first models of the atom.
Okay, so how did they even start putting this atomic puzzle together?
Well, one of the first models was the plum pudding model, thought up by J.J. Thomson himself.
Plum pudding. That sounds a lot more delicious than I expected.
Right. Imagine a bowl of plum pudding where the plums are the negatively charged electrons scattered throughout a positively charged pudding, which is the rest of the atom.
Okay, so the plum pudding model, it's visually a lot more appealing than I thought it'd be. And it kind of makes sense, with the positive and negative charges balancing out and all. But that wasn't the whole story, was it?
You got it. The plum pudding model definitely had its limitations. It couldn't explain what happened in a few groundbreaking experiments, especially this one. They were shooting tiny projectiles at a sheet of gold.
Oh, right. Rutherford's gold foil experiment, right? Isn't that like a classic science story?
Totally. A
Yeah.
total game changer.
Yeah.
So picture this. Rutherford and his team, they're firing these positively charged things called alpha particles, which are basically tiny atomic bullets, at this super thin sheet of gold foil.
Yeah, the PDF was saying how it was only like 1,000 atoms thick. It's crazy.
Insanely thin. So going by that plum pudding model, they thought those alpha particles would pretty much just pass right through those gold atoms, maybe with a tiny deflection, if anything.
Like shooting tiny bullets through a curtain, basically.
Exactly. But what they saw was so much weirder. Some did go through, but some were deflected at these insane angles. Some even bounced straight back.
Wait, seriously? Backwards? What was going on that they weren't expecting?
It was a huge deal. Rutherford even said, it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So the fact that most went through, that made them think, okay, atoms are mostly empty space. But the deflections, those were the big deal. It meant the particles were hitting something small, dense, and with a powerful positive charge.
Like those stones hitting the wire in that fence analogy from the PDF. Most go through, but a couple hit something solid and bounce back.
You got it. And that something was the nucleus, the tiny positively charged core of the atom. That's what demolished that plum pudding model. And that's how Rutherford came up with his nuclear model of the atom.
Okay, so no more plums and pudding. We've got a nucleus now. So are the electrons just, like, orbiting the nucleus like planets around the sun then?
That's what Rutherford thought at first, but there was a problem, something to do with electrons and energy.
Okay. What was wrong with the electrons orbiting like planets?
Well, I mean, classical physics says that any charged particle, like an electron that's moving in a circle, should be losing energy constantly.
So it's like it gets tired and slows down.
Not exactly. It's more like it would be constantly giving off energy, and as it does that, it would spiral inward towards the nucleus.
Oh, like a satellite that loses altitude and crashes back to Earth.
Exactly. But atoms are stable, right? We know that. So if they were constantly spiraling into the nucleus, matter wouldn't exist.
So Rutherford's model, even though it was a breakthrough, basically meant everything was going to, like, self-destruct.
Kind of. Obviously something was missing. Like, what was keeping these things from collapsing?
And that's where Niels Bohr comes in, with the next big breakthrough.
Yes. Bohr's model changed everything. He used this revolutionary idea, quantization.
Quantization. Sounds complicated.
It was a huge shift from what we thought we knew about physics. Bohr said that electrons couldn't just exist anywhere around the nucleus. They had to stick to specific energy levels, almost like, those rings on a dartboard.
Okay, so instead of a free-for-all, electrons have designated areas they have to stay in. I like it. But how does that stop them from crashing into the nucleus?
Because Bohr said that as long as an electron stays in its energy level, it doesn't radiate energy. No energy loss equals no spiraling inward, no atomic collapse.
So Bohr brought stability back to the atom. I've always loved those diagrams of his model, with the electrons in their perfect little orbits.
Those diagrams are helpful, yeah. But we have to remember that's all they are. Visualizations, quantum mechanics is way more nuanced than that.
Right, because in the quantum world, things are never quite what they seem.
Exactly. But before we go too far down the quantum rabbit hole, we've got another piece of this atomic puzzle to find.
What else is there? We've got the nucleus, the protons, the electrons and their energy levels. What are we missing?
Well, it turns out that protons and electrons by themselves don't explain the mass of an atom. There's something else in there. It took a while to find it, though. That would be the neutron.
Right, the neutron. Discovered by James Chadwick, right? No charge, hence the name. But why was it such a big deal to find the neutron?
Because it explained the mass that was missing. See, the mass of an atom didn't add up if you just counted the protons and electrons.
So there had to be something else adding to the mass, but it wasn't showing up as a charge.
Exactly. The neutron didn't just solve that problem, it also opened up this whole new chapter in atomic theory, and that would be the concept of isotopes.
Isotopes. That's where things get really interesting. Before we jump into that, let's do a quick recap. We started with those early clues from static electricity, which got us to the electron and then the proton.
And then we had those first models, like the plum pudding model, which is way more fun to say than it probably deserves to be. And that got us to Rutherford's nuclear model, which was a huge leap forward because it put the positive charge and most of the atom's mass in a tiny nucleus.
Then Bohr came in and said, hey, hold on a second. Electrons don't just spiral into the nucleus. They have their own energy levels. And then right as we thought we had it figured out, we find the neutron.
And as we're about to learn, those neutrons are anything but neutral when it comes to, well, everything. They're important for nuclear reactions, energy production, even how we understand the Earth.
All right, let's talk about isotopes. I'm ready. All right, isotopes. Now, this is where things get really interesting. So we've got these neutrons hanging out in the nucleus now. What does that even mean for how we think about elements?
Well, for ages, everyone thought all atoms of the same element were, like, identical. But neutrons changed all that. See, isotopes, they're atoms of the same element, same number of protons, but with different numbers of neutrons.
So same element, same atomic number, but they can have different masses. Got any examples? I remember the PDF mentioned hydrogen having a bunch of different isotopes.
Oh, yeah, hydrogen was a great example. So your most common hydrogen isotope, which we call protium, has 1 proton, 0 neutrons. But then there's deuterium, which is still hydrogen, because it has 1 proton, but it also has 1 neutron hanging out in the nucleus.
So it's like hydrogen, but like a little heavier.
Exactly. And then you've even got tritium, which has 1 proton and 2 neutrons. Same atomic number, different mass numbers because of those extra neutrons.
You know, I always pictured atoms as these like perfectly identical building blocks. Then you learn about isotopes and it's like, whoa, there are different flavors of each element. But are they just a scientific quirk, or are isotopes actually important?
Oh, isotopes are crazy important. They affect everything from like medicine to how we make energy.
See, now you're speaking my language. I love when something that seems super abstract turns out to have real-world uses. The PDF mentioned something about uranium isotopes being used in nuclear reactors. How does that work?
Well, it's because some isotopes are unstable, right? They have this tendency to decay and release energy when they do. Take uranium-235, for example. That's a uranium isotope. That's what we call highly fissile.
Fissile, meaning?
Meaning that you hit its nucleus with a neutron, it splits and releases a ton of chain reaction, and that's how nuclear power plants work.
Wow. So we're taking advantage of this one specific uranium isotope to generate electricity.
Pretty wild.
Yeah.
What about the medical stuff? I think the PDF also said they use cobalt isotopes for cancer treatments.
Right. Some isotopes are radioactive. They give off radiation that can be used for different medical treatments. For example, cobalt-60, that gives off gamma rays, which are a super high-energy type of radiation that can target and destroy cancer cells. So we're using these tiny little variations in atoms to fight cancer. That's amazing. Something so small can make such a big difference.
It's really amazing. And it's not just cancer. Remember the part in the PDF about treating goiter with iodine isotopes?
Yeah, I thought that was super interesting. We need iodine for our thyroids to work properly, but what do isotopes have to do with it?
Well, our bodies, they can't tell the difference between different isotopes of the same element. So what doctors can do is they can use a radioactive iodine isotope, like iodine-131, and they can track how well the thyroid is taking in the iodine. It helps diagnose thyroid problems.
So it's like a tiny radioactive tracker. That's really cool.
Yeah. And sometimes they even use that radioactive iodine to destroy thyroid tissue that's cancerous or if it's too active.
Wow. Okay, isotopes are way more useful than I ever realized. From powering cities to treating all kinds of medical conditions, they're essential.
I know, right? And the crazy thing is, we're still learning more about isotopes, like, all the time. There's always something new to discover.
That's what I love about science. There's always more to find, more to understand. But even with all this, I have this feeling our current model of the atom, even though it's been so helpful, is still just the beginning.
You might be right about that. The quantum world, the world of electrons and the nucleus, it's so much stranger than anything we can really wrap our heads around.
Well, on that note of mystery, I think we're going to have to wrap up this deep dive. But if you found all this as fascinating as we did, do yourself a favor and check out the source PDF. It's got even more cool stuff in there.
It's definitely worth a read for anyone who wants to really go deep on this stuff.
Until next time, keep those brains buzzing. And remember, there's a whole universe, even in the smallest things.